This is a supercritical fluid extraction system that can be used to extract compounds of interest from a more complex matrix. For example, vanillin from vanilla beans or caffeine from coffee beans. The system is called an SFE 500 MR. SFE stands for supercritical fluid extraction. 500 because the extraction vessel and the collection vessel are both 500 ml in volume. Compared to other commercially available supercritical fluid extraction systems, this one has some unique features. First, it is completely automated in its operation. The competing SFE equipment is operated in a manual mode. Compared to traditional sock slit extraction, SFE offers the use of environmentally friendly CO2, so it's a green technology compared to solvent extraction with a sock slit. Much lower operating costs because you're using much smaller amounts of solvent and thus lower solvent costs as well as lower solvent disposal costs. Much lower extraction temperatures are also used in this system. The critical temperature for carbon dioxide is 31 degrees centigrade, and so one can perform extractions at very low temperatures. This is important when you're extracting thermally labile compounds from natural products. Components of the extraction system include the recirculating chiller. This provides chilled ethylene glycol solution to the heat exchanger. The heat exchanger cools the CO2 before it goes to the pump. When the CO2 reaches the pump, it is a liquid, allowing the pump to deliver denser CO2, and it cools the pump, reducing pump head cavitation. Its maximum flow capacity is 50 ml minute of liquid CO2. This high pressure CO2 can then be mixed with a co-solvent, sometimes called a modifier, and typically that's added in amounts of 3 to 5% from this modifier pump. The modifier can be any organic solvent. The mixed solvents, CO2 and co-solvent, are then sent to a second heat exchanger, and in this heat exchanger we heat the mixture of CO2 and solvent up above 31 degrees centigrade, so it is above supercritical conditions and we now have a supercritical fluid. The mixed solvent leaves the second warming heat exchanger and goes into a three-way valve. The three-way valve can direct the flow either to the solvent extraction system or the particle formation system. When we're using it in the extraction mode, the flow is directed toward the bottom of this 500 ml extraction vessel. The CO2 flows in through the bottom of the extraction vessel, flowing up through whatever it is the extraction vessel contains. It dissolves some of those components. Maybe caffeine from coffee beans, maybe some drugs to be tested from plants from the Amazon. The dissolved components and the flowing solvent leave the top of the extraction vessel and go into the back pressure regulator. The pressure is reduced to about 3 bar. Now, it turns out that the solvation power of a supercritical fluid is directly related to its density and thus its pressure. So when we reduce the pressure, things which were dissolved in the dense high pressure CO2 now precipitate out of solution as a solid. The precipitated materials are swept from the back pressure regulator to the fraction collector, along with the small amount of co-solvent that was added. The flowing CO2, which no longer has any solvation powers, is vented from this vent. Some of the things that this system has typically been used for is cleaning components from chemical residues, separation of low molecular weight oligomers from higher molecular weight polymers, isolation of flavors and fragrances, as well as isolation of pharmaceuticals and nutraceuticals from more complex natural product matrices.